So let's give an introductory example. What I'm showing you over here is a movie that I recorded in Egypt, actually. And what you're seeing over there is the spontaneous formation of stop-and-go waves. This happens over here. Let me see whether I can turn on the laser pointer. So over here, you see there's an entrance, but there's no traffic light. So the stop-and-go waves are emergent. So now you can see it. In some places, cars can go, in other places, they're stopped. And this is always amazing to find, I think. All right. And you know, before all the recording was possible, people were actually collecting data. That was a hand job almost, very difficult to put all of this together. As you can see, now, of course, times are different. There's lots of data, and you can do a lot more about it. So what you see here is, in fact, the formation of a phantom traffic jam, where suddenly, you know, from one vehicle to the next, the speed goes down until cars are really stopped, and we have that stop-and-go phenomenon, right? Okay, then here is one of the overview papers that you may want to have a look at if you're interested in traffic. It's already a few years old, but still has a lot of material in it. What we're interested in particular, of course, is congestion patterns, such as those, and how they can be understood, but also how we can get rid of congestion, right? That will be coming in a later part of that lecture. So the idea that we pursued was that those complex patterns could actually be cut down into so-called elementary patterns that we hoped would be characteristics, and we could basically understand the complex pattern as a composition of those elementary patterns. And so the elementary patterns that we separated was basically those pinned localized clusters, where there's some congestion that doesn't move forward or backward. Then there is the moving localized cluster, that is a little traffic jam that moves backward, actually with jam front, which is a constant speed. It's minus 15 kilometers an hour, one of those interesting traffic constants to know about. And here you see stop-and-go traffic, and you can clearly see that those patterns are parallel, and that's because, again, this traffic constant of minus 15 kilometers an hour comes into play over here. That we call oscillating congested traffic, and finally there is homogeneous congested traffic, right? And all of these phenomena we'd like to understand based on traffic models. And there are different kinds of traffic models. Among them, the car following models are maybe some of them more popular. And one of those is called intelligent driver model. Like many of those models, it depends on the distance and speed of the cars, neighboring cars, and relative velocities too in this case. There's an equation of motion, there's an acceleration equation, and there is a certain relationship for this desired distance, which is a dynamic function that depends not only on safety parameters, but also, for example, on the speed and relative velocity, as you can see. Okay, back to traffic modeling and simulation. So what you see over here is the simulation of a simple car following model along the freeway. We assume actually a circular road of 10-kilometer length, and this is how things change in time. And you can see that even though in the beginning the density was almost homogeneous, after a short time, we see the formation of those traffic jams that have the characteristic speed that I mentioned before. So these are phantom traffic jams in a sense, right? So they seem to have no origin. So the reason for this is actually unstable traffic flow, and the slightest variations in the flow will actually amplify, and there will be a domino effect in a sense that makes everything worse until things happen that nobody wanted, which is a traffic jam, right? Now, the traffic jam then moves backward because in the traffic jam, cars are stopped. They're flowing out at the front, they're added at the end, and so altogether that thing moves backward, okay? Now you can see there's also the phenomenon of metastability of traffic flow. You see it represented both in trajectory presentation and in density representation. Small perturbations in that metastable density area will be fading away, while larger perturbations will actually be amplified. And over here in this graph by Boris Kenner, you can see how things depend on the density. So basically for small densities, we have a stable state, which means that perturbations in the traffic flow will fade away. They will disappear. Then at some intermediate densities, we find unstable traffic, so that the slightest variation in the density will actually be amplified and will cause a stop and go phenomenon that I showed you before. And then left and right of this, there are actually so-called metastable states where things really depend on the size of the perturbation. You have a small perturbation, so subcritical as we call it, it will disappear, while if we have a supercritical perturbation, it will be amplified. And that are the outcomes that you will then find, okay? Now, how complicated things can get, you see in this particular simulation over here. So what we're looking at is a freeway with an on-ramp where some additional cars get in. I can see we're looking here at the situation along the freeway and in the course of time. And so in the beginning, we have apparently stable or metastable traffic flow downstream of the on-ramp. The density is somewhat higher because there are additional vehicles that came in, but everything is very stable. Now, here, eventually, we are reducing the density temporarily. And we would think, well, that can't be bad, right? The density is reduced, so the traffic flow should even flow better. And for some time, it's like this. But eventually, that perturbation is changing its shape. It's growing big. It has already passed the on-ramp, but it returns, which we call the boomerang effect. And then once it comes back to the location of the on-ramp, suddenly traffic breaks down, which means the capacity of the freeway has dropped. Then we find a backlog. It means a queue of vehicles is formed behind that location of the on-ramp. And on top of this, we also have oscillatory congested traffic, right? So there are a lot of things that happen just in this one single simulation. And what you can see over here is that reducing density may actually be bad if that was in the metastable regime and the perturbation had an overcritical amplitude. So it was destined to grow and eventually mess up the entire system, right? And so this boomerang effect that I just described is actually found in many empirical examples. It turns out, however, that there's an additional thing that's going on. And here are some more empirical data about this. We can see that actually the perturbation grows only when it travels backward. Here, the amplitude didn't grow. It's only, as we see over here in that representation, the spatial extension that grows in the beginning, not the amplitude. And only once we get close to this off-ramp, there's a perturbation of cars that are trying to get out of the freeway. This is finally messing up things such that there is a supercritical perturbation that will grow and travel backward, right? That's what you see over here. Now, for a long time, we have wondered what is going on here. So you see two lines over here, right? This line and that line. We're interested in that line over here, the first line. So what speed does that front travel with? What's your hunch? It is 80 kilometers an hour. Now, after I've said this, do you now have an idea what's going on here? So basically what we are seeing here is an overtaking maneuver of trucks. And so basically those trucks will go along the freeway for some time at 80 kilometers an hour and block the freeway. And behind that, there will be a growing jam of cars. So the length extends over time. And this is what happens in the beginning. Then, as I said, cars are trying to get out of the freeway. That produces perturbations in the flow, and those are being amplified eventually, right? So it's the overtaking maneuver of trucks that produces a large perturbation in the flow that is then finally triggering the traffic jam. And in other words, knowing this means that if we forbid overtaking of trucks at certain times of the day, we could actually produce less traffic jams.